So here I'm going to go over problem number 2 from the 1986 AP Physics C Electricity and Magnetism AP exam. So this is an interesting problem. At the beginning you start off with just resistors, and then they end up shoving an inductor in there later in the problem. So starting off, we have 5 resistors connected as shown here, and part A is to determine the current in the resistor labeled R at this point. So this one is simple enough. So first of all, we're going to give some names. We're going to call the path down the left side path 1 and the path down the right side path 2. And in determining that current, well, we need to figure out the equivalent resistance. So we have V equals IR from Ohm's law. So the current coming out of the battery is going to be equal to the potential difference of the battery divided by the equivalent resistance of the circuit. Well, what's the equivalent resistance of the circuit? So going from the battery first, we have a 5 ohm resistor that we encounter, and the equivalent resistance of a series circuit is just the sum of each of the individual resistances. So we have 5 ohms plus whatever the resistance of our rectangle is. Well, the resistance of our rectangle is given by the fact that the inverse of that is going to be equal to the sum of the inverted resistances. So 1 over the rectangle's resistance is equal to 1 over R1 plus 1 over R2. So now, plugging in those numbers, I probably should have given names to the different resistors, but in this case this was good enough. We have 1 over 40 ohms plus 1 over 40 ohms because we have 40 ohms down each path, where each of those comes from the series sum, in this case of 10 plus 30 and 30 plus 10. So 1 over 40 plus 1 over 40 is 1 over 20, so that inverted is just going to be 20 ohms, and that plus the 5 ohms that we had at the beginning here gives an equivalent resistance of 25 ohms. So the current coming out of the battery is 1 amp. But we don't care so much about the current coming out of the battery. We needed it as a way to get the current going down through our resistor R. Well, the resistance of path 1 is the same as the resistance of path 2, so the current going through path 1 is the same as the current going through path 2 because their potential differences are going to be the same. Because you start here, you end here, you're dealing with wires at the beginning, wires at the end, so the potential at this point is the same here and here. The potential right here is the same here as it is right here, so the potential difference along each path is the same. So since I1 plus I2 is 1 amp, in other words, Kirchhoff's junction rule here, which I could have been a bit explicit and listed, that the sum of the currents going into this junction is equal to I1 plus I2. Well, that's 1 amp, so since I1 is equal to I2, each of those must be 0.5 amps, so that must be the current going through resistor R. So in part B, we are now connecting a capacitor between points A and B. So the currents in the circuit and the charge on the capacitor eventually reach constant values. So the question is, part B, what is the constant value for the current through resistor R? Well, here's the thing. Once the current reaches a constant value, that is steady state, that means there's no current flowing between points A and B. So since there's no current flowing between points A and B, that means we have exactly the same situation, at least in terms of current flow, as we had in part A. In other words, the current through resistor R is the same as it was in part A, which is equal to 0.50 amps. But part C, what is the charge that accumulates on this capacitor once it reaches an approximately constant value? Well, here you have your equation, Q equals C delta V. That comes from the definition of capacitance. Capacitance is defined as the charge per unit voltage or charge per unit potential difference. That's an equation you should definitely memorize. If it's at the top of your head, you'll immediately know what to do as you are reading a problem like this, instead of having to fumble around on an equation sheet. Remember, the point of the equation sheet is not to remind you of the equations, because after all, you're supposed to know all of the equations. The point of the equation sheet is to remind you of what your valid starting points are. So here, your starting point is Q equals C delta V, or C equals Q over delta V. Well, the capacitance is given. That's C. That's 10 microfarads. And the potential difference, though, is something that we need to figure out. In other words, the potential difference for that capacitor is equal to whatever the potential difference is between points A and B. But we can figure that out because we know the current going through each of these arms. We know the current going down the left side, we know the current going down the right side. And we know that at the start of this, the electric potential is the same. So the potential difference between points A and B, therefore, will be the same as the potential drop from the beginning through each of these resistors. So we can just write that out. VB is equal to I1R minus I2 times the resistance of that 30 ohm resistor. Now keep in mind that this is not a general equation in this situation. This is an equation that works in this specific instance. Technically, the potential at point A is equal to the potential here minus IR, and the potential at point B is equal to the potential here minus IR. But we're subtracting those, so upon subtracting those, we've canceled out the potential at this point before the junction. So now we're ready to plug in our numbers. I1 and I2 are the same as it turns out. We plug in our resistance values and we get a potential difference there of 10 volts. So now that we know the potential difference and we're given the capacitance, we can shove that into our equation and get that the charge that is accumulated on our capacitor at steady state is 1 times 10 to the minus 4 coulombs, or for those of you who love Greek prefixes, we have 100 microcoulombs. So now, with part D, we replace the capacitor with an inductor. The inductor is an ideal inductor, so the question is now, what are the constant values for the current in the resistor R and the current in the inductor? So this is a different situation than in part A and in part B, because now, even though we've reached a constant value, well, part B was talking about a capacitor. When you've reached a constant value in a capacitor, the capacitor is filled up. There's no current going through it. But when you've reached a constant value, a steady state situation in an inductor, there is current going through the inductor. So we have been good physics students here. We have labeled our diagram with enough labels to help us figure this out. So there are a number of different ways of attacking part D. What you could do is realize, oh, well, this is, once we've reached a constant value here, the potential at point A is the same as the potential at point B, because when the current has reached steady state through an inductor, the inductor just acts like a wire. You could do it that way, but I want to do it in a more general method first, because this will allow us to, if necessary, and it has been necessary in some other years, figure out an equation for the current as a function of time through this inductor. So here's what we're going to do. We recognize, first of all, that at steady state, we have di dt is equal to 0, so there's no voltage drop through the inductor. So points A and B must be at the same potential. Now, it turns out that it's reasonable to suspect that the current is actually going from A to B through the inductor. It turns out it's also correct once that's the result of a calculation that we're eventually going to do. But it's reasonable because of the fact that you recognize there's less resistance from this point that I've labeled C down to A than there is from this point that I've labeled D down to B. So you would expect that more current is going to go along this path than along this path. And it turns out that ends up being correct, as we will find eventually. So, since we've reached steady state, that means di dt is 0, which means that the voltage drop through the inductor is 0, because voltage drop through an inductor is negative L di dt. That's another one of those things that you need to have memorized. So that part is 0. So potential at A is the same as the potential at B, which means that delta CA is equal to delta dB, where I've labeled points C and D above as mentioned before. That, again, is different from parts A and B. In parts A and B, these potentials were not the same. But what that means is that the currents must no longer be the same, because in parts A and B, the currents were the same in each arm. This time, they must not be, which means there's going to be some net current flow. So we have, since delta CA is equal to delta delta V for CA is equal to delta V for DB. That means that I through this arm times this resistance is equal to I through this arm times this resistance. In fact, I should have written that explicitly. I should have said that therefore I1R is equal to I2 R2, so to speak, though maybe I should come up with a different name for that, but I just plugged in the numbers. It turns out in this case that's okay. So the result of this realization is that the current going through R is 3 times the current going through the 30 ohm resistor, which shouldn't be surprising because the resistance is 3 times less. And similarly, we also realize that because of the fact that delta VAE is equal to delta VBF, that means that the current going through I4 must be 3 times the current going through I3, because if the potential difference is the same and the resistance is 1/3 of what it is in the other one, then the current must be 3 times. Again, that's just Ohm's law. V equals IR. Now, by the junction rule, Kirchhoff's junction rule, I, which we've labeled over here, is equal to I1 plus I2. So now we finally made that explicit. Maybe we should have done that a little bit earlier in the problem. Well, what is I2? Well, I know what I2 is. That's up here. I1 is 3 times I2, so that means I2 is 1/3 of I1, so I plugged that in. And now we realize that this I is 4/3 of I1. So therefore, I1 is equal to 3/4 of what the current coming out of the battery is, which means therefore I2 is 1/4 of what the current coming out of the battery is. Now, we also know that I is equal to I3 plus I4, so I4 is 3/4 of the current coming out of the battery as well. So here's what we're going to do next. We're going to consider a loop, because we have some simultaneous equations here, but not enough of them as it turns out. We have more unknowns right now than we have equations, but we're going to consider a loop. We're going to start at the battery and go this way. Start at the battery, go out, the only way we can go so far, but at point C we're going to go down through R, and then we're going to go through the inductor going from A to B, and then from B to F, and then F all the way back to the battery. So that is going to give us the last equation that we're going to need. So here's what we know so far. I1 is 3I2, I4 is 3I3, I1 is 3/4 I, and I4 is 3/4 I as well. So using that Kirchhoff's loop rule, the sum of our delta V's in any loop is 0. That means, so we start off, we have plus delta V for the battery, minus I times 5 ohms, minus I1 times R, minus L di dt, minus I4 times this resistor, and then all the way back. Well, luckily, again, di dt at this point is 0 because we've reached a steady state. So we're ready to plug in our numbers. And notice that now that we've done this, we have everything in terms of I. The missing variable that we needed was the potential of the battery. And we end up getting exactly what we would have gotten if we had just said, oh, A and B have the same potential, so therefore we can treat this just as a wire and get the equivalent resistance along here, which turns out to be 7.5 ohms. Get the equivalent resistance along here, that's 7.5 ohms, add them up, and you get an equivalent resistance for the circuit of 20 ohms. So 1.25 amps comes out of the battery is our result here as well. And now that we recognize that, remember the whole point of this was to figure out the current going through the resistor. So now that we have all that, we plug in that 1.25 amps and we get about 0.94 amps for that current going through the resistor labeled R. Actually 0.9375 amps, but we rounded it using sig figs and stuff like that, assuming that they meant 2 sig figs on all of these. Now, for part E, what is the constant value of the current through the inductor? Well, we have a junction rule here. The current through the inductor is equal to I1 minus I3. In other words, I1 is equal to IL plus I3. That's sum of the currents into junction A is equal to the sum of the currents out of junction A, is really how I should have started that step. So current going through the inductor is I1 minus I3. Well, we know what those are. Those are in terms of the current coming out of the battery. But we know the current coming out of the battery. That was 1.25 amps. So plugging that in, we get 0.63 amps for the current going through the inductor. And by the way, that current's going through toward the right, but they didn't ask us that, but I wanted to mention that anyway. So it turns out that if we had been wrong in our belief about the current going through the right, then we simply would have obtained a negative sign in our answer, but we still would have had the same value at steady state. So that didn't matter for us because we were dealing with steady state. But if they were asking us for I as a function of t, or I, say, like at halfway through or something like that, and we got a negative answer, then in that case we would have needed to start over, because in that case the sign of di dt would have been switched. And we would have needed to start back at the beginning and switch the sign back and then obtain a new answer. So I mention all of this because you should be able to do a problem like that if you were asked to find, say, I of t, or if they asked you what is I at like half of the fully charged time, which is usually taken to be about 5 time constants. You do remember what the time constant for an inductor is, right? Yeah, L over R. So make sure that you remember that also. So that is the end of our presentation of the solution to the problem part number 2 of 1986 E&M. But I do want to go through back again and show where all of the points were given. So in part A, they gave 1 point for noting that V equals IR, or at least some statement of Ohm's law, and also a point for obtaining an equivalent resistance of 20 ohms for the rectangle, the AB rectangle, so to speak, and 1 point for getting the equivalent resistance of the whole circuit being 25 ohms, and then 1 point for getting that current being half an amp coming out or going through resistor R. In part B, they gave simply 2 points for saying the same thing as part A, or 0.5 amps. This is another reason why it's often good to give a short justification of your answer, even if they're not asking for it, because in this case, let's say that you had computed part A wrong and you had gotten 3.14 amps or something like that. Well, then in part B, if you had just listed 3.14 amps without a justification, depending on the day, they might not have given you full credit for that. But if you mentioned that it should be the same as it is in part A and then listed 3.14 amps, you would have gotten those 2 points. I assume that 1 point is for the magnitude of, or at least the value of the number, and 1 point is for the units here. Now, part C was worth a total of 4 points. One of those points was for the equation Q equals C delta V. Another one of those points was for realizing or determining that that electric potential difference there is 10 volts. Now, in truth, you should have shown that calculation. Actually, they gave 2 points for this. So, in truth, yes, you should have shown this calculation. I don't know why they just said 2 points for listing that, but that is what it is on the rubric. And then the 4th point is for finding that that charge ends up being 100 microcoulombs, or 1 times 10 to the minus 4 coulombs. Now, part D, they performed this differently than we did. They simply used the shortcut method of saying that since the potential at point A and B are the same, then we can just kind of merge this together and think of this as first a 5 ohm resistor, then a 10 and a 30 in parallel, then a 30 and a 10 in parallel, and you're done. And so they gave you 1 point for getting that the equivalent resistance of each of these parts that are in parallel is 7.5 ohms, and then 1 point for getting that the equivalent resistance of the whole circuit was 20 ohms, and then 1 point for getting that the current coming out of the battery was 1.25 amps, and then 1 point for the final answer of 0.94 amps. We did it differently. The way we did it was completely valid, and I would actually say is probably in some ways a little bit better because it's a more general method. This method would work even if di dt wasn't 0. So if they were grading it this way, I would say that they probably would have given a point for recognizing that delta CA equals delta dB, and probably a point for getting each of these currents in terms of the current coming out of the battery, and then a point for finding the current coming out of the battery using the loop rule, and then a point for getting the final answer. So they generally do have alternate ways of grading a problem if there's another valid solution that is given. And that's another reason to make sure that you're showing all of your work and being explicit in your steps, because if they're not expecting a certain solution, then you need to make it very understandable for your grader, because you want your grader to be able to understand your work now, don't you? Now, part E, they gave simply 1 point for the final correct answer, being 0.63 amps. Amusingly, the official solution actually has it as 0.624 amps, but I'm guessing that that's a typo. Remember, these solutions were made in 1986. And then finally, for some commentary on that, of course, there were no points given for the commentary, but if you need to see the commentary again, then you can pause the video. But otherwise, if you have any questions, please let me know. Thank you.